Hi, it's Thursday, June 25th, 2020. My name is Noah Seeley, and welcome to my channel. So today we're going to be finishing our discussion on the dueling network architectures for deep reinforcement learning paper by the Google DeepMind's team. This is the second installment for our discussion on this paper, and today we'll be looking at the experiments, conclusion, and discussion sections of the paper. Before we get to it, if anything related to reinforcement learning still seems a little bit fuzzy, I invite you to go check out my two-part intro to reinforcement learning series that I'll link in the description below. They're quick videos and cover the definitions, processes, and applications used in reinforcement learning. There are also a ton of other resources related to coding and machine learning, including a collection of reinforcement learning paper discussions over on my channel. So go check all of that out if you haven't already. Without any further delay, let's review what we saw in the last part and then get on with the rest of the paper. So in part one of this video discussion, we reviewed the introduction, background, and architecture sections of the paper. In those sections, we saw that the Google DeepMind researchers were motivated to make a deep learning network specifically for reinforcement learning, as the networks used before for deep reinforcement learning consisted of those that were originally made for different learning tasks. From this, the dueling network was created, shown here in the bottom of figure 1. It has a CNN that takes an input, which leads to two separate streams. One would estimate state values, and the other would estimate an action advantage function. The architecture then combines these two streams with a special hidden layer that will output a single Q value. As this architecture takes input via a CNN and outputs a Q value, it is able to be used in algorithms such as double Q learning. The agent will also be tested using uniformly sampled experience replay and prioritized experience replay. The inspiration for this architecture comes from the researchers' theory that an action doesn't actually have to be chosen at every single existing state, and when they are, some may become irrelevant. An example of this lies in figure 2, shown here in the paper, which shows saliency maps of the architecture in use. We see that the action advantage stream is only ever active when there is an active objective seen in the environment. This shows that the car only actually needs to move when it needs to get out of the way, and if there are no other cars on the road, any action of moving left or right is actually irrelevant, and thus by separating the state thinking and the action thinking, we can make a more efficient agent as these irrelevant actions are reduced. So yeah, if you want a deeper look at any of those topics, I'll link part 1 of this video in the description below. If you feel all caught up though, let's finish off this paper. The experiment section starts off with a subsection devoted to testing policy evaluation. The team says that policy evaluation is very good at evaluating network architectures. They use a similar update rule from an algorithm called expected sarsa, and the environment used for testing is called the corridor, and consists of a task which requires the agent to move all the way through a corridor in order to gain the maximum reward, all while only using a small action set of up, down, left, right, and do nothing. They use a greedy policy, which basically has the agent choose the action that will yield the most optimal Q function, so the max of the Q values that are directly available. They compare various performances between a single streamed Q architecture and the dueling network with the corridor task, using the squared error as a performance measurement. Shown here in figure 3 in the paper, the results of this comparison show that as the number of actions increase, the dueling network will converge faster than the single streamed architecture. The next section describes the comparison of the single stream Q architecture and the dueling network in Atari games. They use the arcade learning environment, which is a challenge where one agent must learn to play 57 Atari games, all while using the same architecture, algorithms, and hyperparameters across all games. As described in the part 1 video of this discussion, the agent is comprised of a CNN for visual game input of the environment, which follow the two streams that we now know and love, and lastly a fully connected hidden layer for output. The model also uses the double DQN learning algorithm. It will be put up against a single stream DQN network, which will be trained with the same learning algorithm as the dueling network. Basically, they just actively try to keep these agents as similar as possible in order to isolate the difference between the two networks used. They start the agents in random starting states of the game and measure improvement in percentage in score over the better of human and baseline agent scores. Finally, the moment we've all been waiting for, shown here in figure 4, the dueling network is shown to outperform the single streamed architectures which it was being compared against, showing dramatic improvement across around 75% of the games played. So with that being said, the robustness of human starts subsection describes how the dueling network is able to generalize to games, given they start randomly according to human experts, and outperform the single stream architecture during comparison. The prioritized experience replay section shows the team's final experiments with the dueling network, which was meant to investigate its performance while using an implementation of prioritized experience replay. They set up the same agent, except for this time it was implemented implemented with a prioritized experience replay, and compared it against the previous implementation of the Dueling network agent and another baseline single-streamed agent that also used prioritized experience replay. Figure 5 shows that the prioritized experience replay significantly improved the performance of the Dueling network, as it outperformed both the original Dueling network and the baseline agent. And lastly, the saliency map subsection simply reiterates what was discussed in the introduction section from part 1. The team computed saliency maps to further show the significance of an action advantage stream. As shown as an example in figure 2 that we saw earlier, the value stream pays attention to the general environment, especially the ever-changing horizon, where new cars would affect future behavior, as well as the score, while the advantage stream will focus more on the immediate objective, which requires actions, such as the oncoming cars. The discussion section discusses the advantages of the Dueling network, which they say is that it can update its state value stream every time a Q value is updated. This contrasts single-streamed architectures, as they only update the value for one action, the rest remaining untouched. They say the more frequently the value stream updates, the more resources will be allocated to the V function, which allows for better approximations of the state value. By separating the state and action streams, the agent was able to reduce a lot of noise in both, as the scaling of updates for both state values and action values are usually much different and update at different speeds. These theories were backed up by the fact, as seen in the experiment section, that the Dueling network agent was able to outperform a single-streamed Q learning agent during relatively standardized testing. The conclusion ends the paper by showing how the team was able to build a new network specific to the field and make a state-of-the-art agent in its domain. This seems to follow a trend of the Google DeepMind's team, as they continuously try to improve their agent by constantly implementing new strategies to improve its learning and performance. In the case of this paper, the improvement was to make a network that was specific to the field of reinforcement learning, in order to separate the agent's thinking into two streams, which would ultimately make it more efficient and, as the team put it, state-of-the-art. So yeah, that wraps up our discussion on the Dueling network architectures for deep reinforcement learning by the Google DeepMind's team. Today we covered the experiments, discussion, and conclusion sections. I hope you've learned something in this paper, as it's very important to continue to think of different ways to improve agents as we look more and more into reinforcement learning. There were also some more technical bits in today's sections that I did not delve as much into, so as always, I've linked all resources in the description below for you guys to go check out yourselves. If you feel that I've missed anything or got anything wrong, please let me know in the comment section below. That's all for today. Thanks for watching. See you tomorrow.